this talk is based on the joint work with Norihiro Iizuka-san and Kengo Maeda-san. And these two papers, recent papers last year and last year. Okay, so I'm interested in that we are concerned with always energy and causality when we consider physically reasonable, sensible systems. Energy and causality are basic notions in physics. And for any reasonable physical system, we expect energy should be positive or maybe zero, what even can be negative, but at least it should be bounded below, because in that case, only in that case, we can have a stable ground state for a physical system. And in general relativity, basically energy can be, well, some conditions for energy should be defined in terms of what is called stress energy tensor, T mu nu, this one. And also we have to specify the observers, well, I denoted by Guzi, because we are concerned with who can measure the energy density. Okay, so by specifying the stress energy tensor and specifying the observer, we can introduce some certain energy conditions. And as for a causality, we are concerned with some field propagation, and any physically reasonable field should propagate in a causally well-behaved way. And causality in a general relativity, or maybe in, well, special relativity, causality is governed by light cone. But when we are interested in curved space-time, global causality is actually governed by achronal null geodesics. I'm going into this, what this achronal null geodesic means later. Okay, so in this talk, I'd like to examine the compatibility of energy conditions and global causality in the context of AdS CFT correspondence. So this cylinder, this describes conformal diagram of AdS space-time. So this inside the cylinder corresponds to AdS bulk space-time with negative cosmological constant, and the boundary cylinder corresponds to what to say, static Einstein universe in a global sense. But you can also take a flat Minkowski space-time as a boundary if you just restrict your attention to some certain area, okay, certain regions. And using this AdS CFT correspondence, I'd like to explain how to derive a certain type of energy condition. In particular, we'd like to derive the ANEC. This is the abbreviation, the averaged non-energy condition on curved boundary space-time case. Okay, this is the main purpose. And I think because we have the audience from not only from the GR, general relativity, but also from various different areas in physics. So I think it's good. I think it's a better idea to start with some brief review of some basic notions. It's often used in GR, but maybe some technical jargon. So I'd like to first briefly explain what non-energy condition is and its important role in general relativity. This is the first part is just a review. And in the second part, I'd like to explain how to derive average non-energy condition. This is a particular type of energy condition using AdS CFT correspondence. This is my plan of talk. Okay, so non-energy condition and its usage in general relativity. Before going into non-energy condition, let me explain the maybe 4 types of energy condition. So in general relativity, we use the Einstein equation, and the quintessential quantity is a stress energy tensor in this context, and that appears in the right-hand side of this Einstein equation, some matter field. So this stress energy tensor is composed of, for example, energy density measured by local observer, and also some pressure, and maybe some momentum, energy flow, and anisotropic stress and so on. And but for simplest case, like a Friedman cosmology, stress energy tensor can just be described in terms of energy density, for velocity, normalized for velocity, and the pressure term. And perhaps from the physical viewpoint, perhaps the most important condition for the energy is what is called weak energy conditions. So you choose time-like vector field, Z. This is a tangent, or maybe a tangent vector for the world line of the time-like observer. Even the time-like means a massive observer. And then you dot a stress energy tensor with this vector field and impose the non-negativity of this one. And this is standard, and perhaps from the physical point of view, most important energy condition. And this weak energy condition is known to hold for any classical matter systems. Okay, and second one, this is not important in my talk, but just let me introduce. So the dominant energy conditions, that is in some sense, this is similar to this weak energy condition, but this is more relevant in when you formulate the conservation theorem in not just a local one, but in some finite region, you can formulate a conservation theorem, and then you have to use this dominant energy condition. Okay, so basically it means that the energy density should be greater than or equal to the pressure, the magnitude of the pressure. Okay, these are energy conditions introduced from the physical point of view. And next, I'd like to introduce the two energy conditions they are introduced from the geometric viewpoint. So the first one is strong energy condition. Looks like weak energy condition, but a little bit different. This Z is again the vector field tangent to the time-like observer, and this actually governs the focusing of the time-like geodesics. Time-like geodesics is always pulled together because due to the gravitational attraction. Okay, and the second yes, and the next one is in some sense the limit of this one. So this is a null energy condition. In that case, you just consider null vector field and dotted this stress energy tensor with this null vector k and impose non-negativity of this quantity. This governs null geodesic focusing. So you consider two or many null geodesics, band of null geodesics, and they are focusing due to the gravitational pull. And this is actually a null geodesic limit of the weak energy condition. So if this null energy condition is violated, then you can immediately find that weak energy condition will also be violated. So from the physical point of view, this null energy condition is also important. Okay, so null energy condition, and from now on, I just focus on null energy condition, often abbreviated by NEC. And this plays an important role in general relativity. So this is actually dotted with null vector field. So this NEC implies that the positivity of energy density measured by locally fastest observers. Locally fastest means that the observer has the speed of light, moving speed of light, like this. Okay, and this governs the focusing of null geodesic congruence. Congruence means the bundle of geodesics. And so geodesic is a free particle orbit. So null geodesic congruence can be viewed as ideal probe field. Ideal probe field to probe the space-time geometry. So by examining the behavior of this null geodesic congruence, we can learn a lot about the space-time geometry we are interested in. So it's very important. And this energy condition, null energy condition, is used in an essential way in proofs of number of theorems, important theorems in general relativity, such as celebrated singularity theorems, black hole area theorem, and topological censorship, and so on. And as for an example, let me briefly explain how this null energy condition plays a role in the proof of black hole area theorem. Okay, so this lambda is actually a affine parameter, well, some standard natural time parameter of null geodesics. And as a directional derivative, you can define the null vector field K. And then define the expansion, classical expansion as a divergence, for divergence of this null vector field. Then actually, this is equivalent, you can see that equivalent to what to say, area difference, the change of the area. Look, and the area is a cross-section area of this bundle of neural geodesics, I mean the neural geodesic congruence. Okay, as a simplest example, let's consider some null geodesic emanating from some fixed radius two sphere in flat space-time, in four-dimensional flat space-time. So it's a radius of R. And you have the 4 pi R square, that is the area of this sphere. And then you consider, okay, let's consider outgoing null geodesics, or maybe just light rays. Then because R is actually a affine parameter, so using this formula, you can compute expansion and becomes 2 over R. 2 is a dimension, describe the dimension of this area of the wavefront. And clearly this is positive. That implies that the sectional area of the wavefront is increasing, expanding. And also you can consider the ingoing light rays, and the light rays, the cross-section area of this wavefront of the ingoing light rays actually decreasing, and that can be quantified by computing this ingoing expansion. Well, so expansion is now negative. That implies area is getting shrinking. Okay, this is a space-time picture of this, the same thing. So outgoing, we have positive expansion, and ingoing, we have negative expansion, what maybe contraction. But outgoing is not always positive, because if you, for example, consider curved space-time, highly curved space-time, like a black hole, in that case, in particular, if you consider inside a black hole, because of this highly strong gravity, even the outgoing expansion, the outgoing neural geodesics becomes negative. So even outgoing wavefront is shrinking. So in that sense, this expansion measures how the gravity is strong. Okay, and this expansion actually is governed by Raychard equation, called Raychard equation. And this is lambda is affine time, and then the different the affine time change of the expansion is governed by the right-hand side, and all the time, you can forget about sigma squared. This is shared, but all the term has a minus signature. Therefore, once at some point you get a positive null energy. Null energy means that energy density measured by null observer. If this is a non-negative, then always this derivative of expansion is negative, or maybe 0 or negative. Therefore, this implies that if at some point initially expansion is once get negative, then eventually expansion becomes minus infinity. Minus infinity because implies that the sectional area becomes 0 at some point. And this point is often called conjugate point, but also sometimes called focal point, or maybe you can call it caustic. Okay. So this is the focusing theorem. whenever the no energy is positive, no energy constant holds, you have a conjugate point. And focusing of the no geodesic congruence. This often occurs whenever no energy condition neg is satisfied. And also when some generic condition is satisfied. I don't go into this no energy condition, but basically there are not much symmetry, space-time symmetry. The space-time is quite general. In that case, well, any geodesic can feel some tidal force, gravitational tidal force. And also at some, or maybe at some point, once the expansion becomes negative, then eventually expansion of such a no geodesic becomes minus infinity, and you get here some focusing point, conjugate point. This is a light cone, but because of space-time is a little bit curved, so you get some caustic. And this is not wrong, and actually this is quite natural. It often occurs in our universe right out there. It's quite natural things. However, this shouldn't occur along the, for example, some black hole event horizon. So event horizon, black hole event horizon, or maybe a cosmological horizon. Anyway, some kind of boundary of the causal set. In that case, because of the causal nature of the horizon, this kind of caustics or conjugate terms shouldn't be allowed to occur in the future direction. For example, in the black hole horizon case, this caustic shouldn't occur in the future because the black hole horizon is a causal boundary of the causal path of the infinity. Therefore, if no energy condition holds, then this implies that expansion of this no geodesic along the black hole horizon must be non-negative. But then this in turn implies the area must be non-decreasing. This is the basic idea to prove the black hole area theorem proven by Stephen Hawking a long time ago. And this is based on the idea of the subsequent Bekenstein's interpretation of the black hole entropy, area entropy, like this, and also motivate to some generalization toward including such as fundamental entropy or entanglement entropy outside the black hole, and consider some generalized entropy and the generalized second law, and create many related researches. Okay, so this is one of the most important applications of the NEC, no energy condition. All right, and let me add another interesting application of this no energy condition, namely what is called no bulk shortcut theorem, or maybe a Gao and Wald theorem. This is very relevant to the rest of my talk. Okay? So let me briefly explain this, what this no bulk shortcut theorem implies. Okay, so from now on, we are interested in the AdS CFT correspondence. So let's consider some AdS spacetime. So this is this one is a conformal diagram of AdS spacetime, global AdS spacetime, and this cylindrical part, this is a boundary. The boundary is a kind of closed universe, closed static universe, like often called Lorentzian cylinder. Well, yes. And consider two boundary points, P and Q. Sorry, how to remember this? Oh. Sorry.
What happened?
Okay, it's okay. Okay, let's consider 2 points, P and Q on the boundary, like a cylinder-like boundary, and suppose these 2 points are connected by achronal non-geodesic gamma. Gamma is entirely lying on the boundary, Therefore, this is null geodesic with respect to the boundary spacetime metric. Okay. And aclonal, I added a aclonality. The aclonal null gamma. What the aclonality implies that the gamma is the fastest null geodesic among null geodesic in boundary spacetime. Okay, so that means not aclonal means not clonal. So no 2 points on the gamma can be connected by a boundary time-like curve. So there's no 2 point time-like separation. And if you consider any null geodesic in Minkowski spacetime, in that case, null geodesic is aclonal. But if you consider curved spacetime, in particular highly curved spacetime, then it's not always the case. In particular, if you consider the black hole spacetime, highly curved spacetime, not all null geodesic is aclonal. A typical example of the non-aclonal null geodesic is like this. This is a picture of the black hole shadow taken by the Event Horizon Telescope team, and this is the light. You can see the light rays from far from somewhere in the universe traveling near the black hole, and it may goes around the black hole near region and eventually come to our eyes. Okay, so in some sense, such a non-aclonal null geodesic or clonal null geodesic simply is what takes some detour around the black hole and eventually come to us. Okay, this is an example, simplest and visual example of the non-aclonal null geodesic. Okay, so the aclonal. Anyway, aclonal null geodesic is the fastest geodesic. Okay, suppose. Okay, so this is the fastest among any geodesics in boundary spacetime, but we also have the bulk spacetime inside this boundary. Then suppose there is a bulk shortcut time-like curve that anchors to 2 points P and Q. GZ connect P and Q, but still this GZ is time-like. In that case, we can call GZ as a GZ, the bulk shortcut. But then it implies that because GZ is just a time-like, there's no curve is faster than time-like curve. Therefore, the boundary point P can be connected with a boundary point R, which is strictly passed to the point Q, connected by some bulk causal curve, like a dashed line, possibly null geodesic inside the bulk, and possibly aclonal null geodesic with respect to the bulk metric. Okay, suppose this occurred in an AdS CFT correspondence and dual bulk spacetime, but that is a problem. That causes a problem, because if that is the case, then it implies that bulk propagator could carry information faster than the boundary propagator in this AdS CFT correspondence. So this doesn't give a sensible causal property for the bulk boundary AdS CFT correspondence. So it's not a good property. So we'd like to avoid such a situation. So here we have 2 basic questions. The first.
Sorry. I have a question.
Yes.
So that is correct for brain world context?
In a brain world context, if you have
the setup.
Yeah, if the brain world if the brain world is bended in a strange way, violating some certain energy condition, then it might be possible. But I'm not quite sure what happened in a brain world case. But I think I guess to get such a pathological situation, you have to impose some unhealthy energy condition, I guess. But no, wait.
So as you may know,
maybe even rather standard energy conditions, still you might have that kind of situation inside, because the brain world is actually some surface inside. But as I said, just well, I'll be talking about Gao and Wald theorem, and that theorem applies to quite a general situation, not just the AdS CFT correspondence case, but also some a little bit general cases with some time-like boundary space-time in a containing some bulk space-time. So you have to, so maybe that you are bound, your strange brain world model have to violate Gao and Wald's theorem, no bulk shortcut theorem. So at least maybe bulk itself must violate no energy condition.
So as you may know, Ishihara-san discussed this kind of for the Friedman Robertson Walker brain. So it's that argument. There's some mistake in that argument.
No. So the brain world is actually not on the boundary, but inside the bulk. Therefore, even if you consider the standard type stress energy tensor on the boundary, then still reasonable one. Still, maybe you get the faster bulk null geodesic is apparently faster than superluminal than the null geodesic confined inside the brain world. I think you get such a situation.
Okay. Thank you.
I think. Yeah. Thank you. Thank you very much. Okay. So given the boundary metric, I mean, boundary means the conformal infinity, not the brain world inside, but the boundary metric. What kind of effect on the boundary field theory does a sensible bulk causality give rise to? Namely, sensible means no bulk shortcut. And second question is, what kind of boundary metric admits such a pathological bulk shortcut? And to answer these questions, I think the key notion is a average no energy condition, ANEC. Okay, so let me introduce Gao and Wald's theorem. I call it a no bulk shortcut theorem, but basically precisely formulated by Gao and Wald a long time ago. And they imposed a bulk null energy condition, then, and also as well as some reasonable conditions. For example, no naked singularity and those kind of things. And then you can't find a causal propagation. So no bulk shortcut. So for example, if you apply this theorem to a AdS CFT setup, then if the P boundary 2 point P and Q are connected by acronal geodesic lying on the boundary, then there shouldn't be any causal curve inside bulk that can be a shortcut. Okay, so this situation, this pathological situation, the bulk propagators carry information faster than the boundary propagators. Such a pathological situation is not allowed. Oh, okay. And okay, under certain situation, and suppose the bulk space-time satisfy the null energy condition, and still you have a suppose still you have some bulk shortcut. In that case, we can show that actually there must exist a naked singularity. I mean, a singularity naked means the singularity can be seen from the boundary observer. For example, the point Q. So singularity is not hidden inside the black hole event horizon inside the bulk. Okay, so this is the case. Okay, so no energy condition is very important, but however, quantum effect often invalidates this neck. So for example, not only neck, actually any locally formulated energy condition can be violated by taking into account the quantum effect. And local energy, no energy condition is easy to violate, like Kashmir energy and so on. And so people propose that non-local non-locally formulated energy conditions, such as average no energy conditions. In this case, you can just integrate this energy condition along a complete no geodesics, so that at some point, at some local point, this local neck is violated, but still the negative fluctuation of this no energy can be compensated by a positive quantum fluctuation at outside region, outside the other part of the no geodesic. So in average, it can be non-negative. This is the idea. However, for some situations, again, even this non-locally formulated ANEC can be violated. Okay, so and some other for it's called aclonal ANEC is also proposed. I'm not going into this aclonal ANEC, but ANEC is very important. It seems nice, but still there are some counterexamples to this. Okay, so the quantum field effect can violate NEC as well as ANEC. Okay, so the non-counter example of the ANEC is constructed as follows. So you can consider CFT, for example, CFT. Yes, in a conformally flat space-time, and find some local violations of no energy condition, like this blue-colored region, some no energy condition locally violated. But then you can enhance this negativity by taking conformal transformations so that this negativity cannot be compensated by other part of the positive energy no energy fluctuations. That is the construction of counterexamples to the ANEC. Okay. So please. Ukajin-san, please.
So I got confused. So this, ANEC is a direct consequence of positivity or relative entropy. So why it can be violated?
Why? So I don't. I have to consider this example, the counterexample in a viewpoint in the context of the this relative entropy. So maybe there's no. It might be difficult to connect this counterexample to the discussion, the argument of relative entropy. I don't have any prompt answer to that, to your question. But anyway, there are some counterexamples using the trick, the conformal transformation trick, to enhance the negativity of the local violation of the neck. You can consult with these papers.
Okay. But probably the punchline is you are not considering a flat space, and so this ANEC beta doesn't show up in the first order deformation of relative entropy or some key, probably.
So actually, I'm going to talk about the curved space-time case, and in the flat space-time case, well, ANEC is shown. ANEC for various fields and various configurations are shown. There are many proofs, but basically you have to consider what is called self-consistent ANEC. So if you consider ANEC or just aclonal ANEC, that can see just on the background space-time. The background space-time, for example, Minkowski space-time, in that case, you completely ignore the back reaction of the quantum stress energy tensor. In that case, you have the counterexample of the ANEC. But if you consider what is called self-consistent ANEC, that means you consider the geometry as a back reacted from this quantum stress energy tensor. You have to solve the semi-classical Einstein equation. In that case,
I see. So maybe my assumption was wrong. I was turning off the gravity, and then so just talking about this, the CFT. But you are considering a system where this CFT is coupled with gravity. That might be the difference.
Actually, in my case, in fact, I'm talking about curved spacetime ANEC, but because I'm using AdS CFT correspondence, that means the background geometry or the boundary geometry is irrelevant to this source energy tensor, renormalized source energy tensor, because in the AdS CFT context, there is no Einstein equation on the boundary, basically. So I don't consider self-consistent ANEC. I just consider ANEC on the fixed boundary spacetime.
Okay.
So it can possibly be violated. Okay. I don't find such example, but possibly be violated. But you could find a counterexample. But
all right, thanks.
Excuse me, Takayagi-san is also has
a question. Yes,
my question is related to point. So for flat space, I think the existing proof is for flat space, only for flat space.
Flat space,
do you think also some program for flat space?
I think in the flat space time, in that case, the ANEC is not self-consistent ANEC, because ANEC implies a stress energy tensor, expression value of the stress energy tensor is the positivity of this one. Yes. But then, if you take into account the back reaction and solve the semi-classical Einstein equation, then the spacetime must differ from the Minkowski spacetime. So that is not a self-consistent ANEC, but ANEC, the standard ANEC, on the fixed background. So that's I think the starting point is different.
So
some people
for that case, I mean, for just a fixed background, just fixed flat space with just matter, that case ANEC is satisfied?
I think so.
I see. But because we are taking into account back reaction, so that changes us. Thank you very much.
Thank you. Okay, so in the rest of the talk, I discussed the compatibility of the bulk boundary causality and the AdS CFT duality. Please go ahead.
Numatsu-san.
Sorry, but so I think so ANEC is also violated. For example, in the 1+1D CFT on a cylinder.
Yes, because of Casimir. Yes, that's right.
Because of Casimir, so there is negative average energy, but that is not acronal null geodesic.
I'm going to talk about I focus on the cylinder case. Therefore, the spatial section is compact, so you can expect the Casimir effect. For example, in that case, ANEC must be violated. But I'm yes. But so in that case, you have to consider what is called aclonal ANEC. Aclonal ANEC. That means you impose ANEC type energy condition only for a restricted class of null geodesics, namely aclonal one. So in a generic spacetime, basically no aclonal null geodesics. So people try to impose this ANEC for any null geodesic. In that case, you get some counterexample, some violation of the ANEC, but just restrict to a clonal one, then you don't have a violation of ANEC, even, yes, at least enough for a self-consistent ANEC. And I'm using this property, the aclonal property in a cylindrical space-time, and then derive this averaged an ANEC. But that may have some counterexample if you consider some. Actually, we have constructed some example that about our ANEC, but that such example is highly deformed. Yeah. So also I'd like to I should mention again that, as I said before, actually our ANEC is not self-consistent. That means we don't take into account any back reaction from the source energy tensor. So this is such a not self-consistent ANEC can often have some counterexample. Let me extend our point later. Okay, so in this case, we derived ANEC with a certain weight function on the boundary covered space-time. And in odd dimension, actually, it is conformally invariant. So we call it KNEC. And because we should have this in our mind. So the counter example of the ANEC is considered by considering conformal transformation. And this trick works because ANEC itself is not conformally invariant. That is the point. That is the point. So we'd like to derive some conformally invariant ANEC. Okay, so now let me turn to the explanation of how to derive the ANEC from AdS CFT correspondence. Yeah, maybe I have 10 minutes or some 15 minutes. Okay, so let's consider D plus one dimensional asymptotical AdS metric. For simplicity, we can just consider some vacuum case, only negative cosmic constant. Then in the standard way, we can assign this kind of Graham-Pfefferman coordinate system. So D equals 0 corresponds to conform infinity because in that case, the metric diverges. So it corresponds to conform infinity. Okay, and this G hat mu nu, this corresponds to D-dimensional hypersurface, I mean a time-like hypersurface, and at the bound D equals 0, this corresponds to boundary metric. And we can expand this G mu nu hat in terms of D. And for the even dimension case, you may have this logarithmic term, but in the odd dimension case, you don't have this. So basically, we have some Taylor type expansion of the metric boundary. And then there is a well-known holographic renormalized stress energy tensor formula. We can consider with this famous paper by the Hall, Sorokin, and Skenderis. So the boundary stress energy tensor can be given in terms of the D part of this Graham-Pfefferman expansion, plus some X, some smooth tensor field. And this corresponds to a gravitational conformal anomaly. But fortunately, this vanishes in odd spacetime dimension. I mean, odd boundary spacetime dimension. Okay. And actually, using this scheme, the ANEC is derived in using the AdS CFT correspondence on the Minkowski background. In this case, in the Minkowski, because the boundary, you can constrain the some certain flat part in the entire boundary, cylindrical boundary. On that flat space-time, any node curves are complete and achronal because it's a Minkowski space. So all node geodesic is the fastest node curve. Okay, so we'd like to, using a similar technique, but we'd like to consider a curved space-time version of this one because we are sometimes interested in the self-consistency and want to get some insight into the what happened for the, if you consider self-consistent ANEC. However, if you consider curved space-time case, then achronal node curves are limited. And this above formula for the stress energy tensor becomes quite complicated, involving the background curved boundary metric and the curved boundary curvature, and also some source terms. So the formulas become quite complicated. Okay, so for the simplicity, let's consider a four-dimensional bulk spacetime, just an AdS bulk, regular entirely, and consider three-dimensional bulk spacetime. Bulk spacetime is just a static cylinder or Einstein static universe. I just put the double node coordinate U and V. They are coordinated on the three-dimensional boundary. And inside the bulk, because we have only a cosmological constant, so no energy condition is obviously satisfied. Therefore, no bulk shortcut theorem holds. Okay, we don't have any bulk shortcut. Okay, let's consider some achronal node geodesic along this v-axis U equals 0 line, and consider some Ricci tensor and compute these quantities. And then let's consider some 2 points, P and Q, and P here at the origin, and Q is actually the sorry, Q should be here, somewhere here, as an antipodal point of the P, because this is a boundary, the global boundary is a closed universe, static universe. So you have a antipodal point Q, and then gamma is a non-geodesic, but at least between P and Q, this gamma is achronal. If you extend this gamma beyond this antipodal point Q, then it becomes chronal. I mean non-achronal. Okay, but between P and Q, it's achronal. Okay, now let's consider 2 point R on this either future of the Q or the past of Q, and try to connect these 2 points P and R, either this one or this one, using a bulk causal curve GZ like this. And you have two choices, A and B, two choices. But B, the path B is not allowed because R, in that case, the point R is passed on the point Q. Therefore, and the P and Q are connected by boundary achronal non-geodesics. And go onward, no shortcut theorem holds. Therefore, the point R must be in the future of Q, well, at least the same point. So therefore, the coordinate value of R must be non-negative. Okay, we start from this fact. Okay. Now consider the tangent vector of this bulk causal curve GZ. It can be like this, 4 components because the bulk is 4 spacetime dimension, and consider some deviation from the boundary gamma, and a deviation vector of the boundary gamma and the bulk causal curve GZ. And this deviation vector, or maybe bulk Jacobi vector, can be expanded by some small parameter epsilon. And this also, we have some other property, other conditions at hand. Because this GZ is a causal curve, so if you contrast with a bulk metric, then the norm of this K, the tangent vector, should be negative or maybe 0, either time-like or no. Then starting using these inequalities, we can derive at the second over epsilon, this bulk Jacobi field behave like this. So when lambda is 0 or √2 times pi, here antipodal point Q, D1 must vanish. This behavior looks just like a boundary Jacobi field. Okay, you can also consider the non-geodesic congruency on the boundary as well, and then consider Jacobi field, and you can derive the equation for the Jacobi field, and they look just like the same. So at the third order, we have this inequality. So this G3 is a component, third component of the Graham-Fefferman expansion. Graham-Fefferman expansion of this quantity, the third order. And according to the holographic renormalized stochastic tensor formula, in a three-dimensional boundary case, this D3 precisely correspond to the boundary stress energy tensor. So you can replace this as a boundary stress energy tensor, renormalized one. And also, we can derive the boundary Raychaud equation. You can just write down, then you can compare the boundary Raychaud equation and the equation for the bulk Jacobi field. They are precisely the same. And also they satisfy the same boundary condition. Therefore, we can identify the bulk Jacobi field D1 and the boundary Jacobi field eta, boundary scales. Then by these identification of this identification and this identification, we get from this quantity, this inequality. So this is what they say. So eta is a magnitude of the Jacobi field. And so not just a standard ANEC, but this is a ANEC with a certain weight function, eta cubic. This is, so we have the positivity of this quantity, average quantity, and integrated from the north pole to the south pole. So the between the 2 points of the antipodals. And in fact, because using this conformal transformation formula, we can check that this quantity is actually conformally invariant. Okay, so I just discussed a simplest case, namely the boundary, just what to say, standard Einstein static universe case. But if you can also consider time-dependent closed universe or that kind of non-trivial boundary geometry. Even in that case, at least for a 3-dimension boundary and 4-dimensional boundary case with positive spatial curvature, we derived actually this conformally invariant ANIC, the ANIC with certain weight function composed of Yukawa field. They are conformally invariant. Okay, so these quantities are given in terms only of the boundary quantities, and also these inequality can be used to restrict the extent of the negativity of the no energy. And because this is conformally invariant, therefore the trick of the conformal transformation to used for constructing the counterexample of the ANIC, that doesn't work. That in that trick, even under that trick, still this KNIC holds. So in that sense, this might be much more useful than the standard ANIC. Or maybe 3 more minutes or something like that. Okay. So far we have focused on the odd dimensional boundary case, and we can extend this analysis to the even dimensional case. But in that case, you have to deal with conformal gravitational conformal anomalies, which makes the relevant forms much more complicated. So this is the holographic renormal stress energy tensor formulas, but you now have this boundary gravitational anomaly term, x mu. This involves a lot of boundary geometric quantities. So fortunately, in the boundary 2-dimensional case, we obtained the standard ANIC because the formula is rather simple. However, in the 4-dimensional case, we don't have the ANIC, but we have some ANIC type inequality with a lower bound like this. The right-hand side, something like this. We express in terms of some geometric quantities like a boundary expansion, the boundary neurodesics, and the boundary quasi-local mass. Well, we assume that spherical symmetry on the boundary. In that case, we can introduce a boundary quasi-local mass density. So for example, if the curvature of the boundary is small enough, in that case, this lower bound is governed by this quasi-local mass density of the boundary space-time. Okay, and in the standard Einstein static cylinder case, we have this inequality. Therefore, we reduce to the standard KNIC. Please go ahead. Show me some, please.
So the lower bound has some physical meaning.
Yes. Well, in this general expression, we have no idea. Yeah. But if you consider, for example, inside the bulk, so for example, you can consider instead of pure AdS, for example, Schwarzschild AdS in that case. In that case, precisely this KNIC with lower bound, KNIC type inequality provides the positivity of the mass parameter.
Oh.
So I think maybe, well, we don't go into further, but I think maybe this example suggests there's a no-bulk shortcut theorem that may be deeply connected with the positive mass theorem in the bulk.
So that term maybe written in terms of Weil tensor.
Possibly related, I think. So you can define the global charges of the bulk AdS asymptotic AdS space-time. For example, in the Schwarzschild AdS case, you have the conserved charge at the boundary, and that corresponds to the bulk wall electric part of the bulk wall curvature, right. Just like a standard Brine-Wald case. Yes, standard formula. And that's one curvature in the bulk can be what to say, maybe taking a Gauss-Kodachi formula or something like that, maybe related to the boundary quantity, like a curvature term and these kind of things. And that then maybe one can find some connection, a little bit more clear explanation. But at this point, we don't have any nice explanation for this quantity. Okay, so, okay. Maybe I have some, I'm running out of time. So some comment. So actually we can construct a counterexample of this quantity. And in that case, however, the boundary should be highly deformed and similar ANEC type inequality where the lower bound is also derived in other contexts as well, field theoretic viewpoint. Okay, let me summarize my talk. So we have pursued the question of what is a sensible causal interaction between the bulk and the common boundary using the Gauss-Novak theoretical property as a guiding principle. And we derived KNEC, conforming invariant no energy condition. And even for the boundary, odd dimensional boundary case, and even dimensional boundary case, we have a similar KNEC type inequality, but with some certain lower bound described in terms of boundary quantities. Okay, I should stop here. Thank you very much.
Thank you very much, Ishibashi-san. So now the session is open for questions and comments. Aoki-san, please.
Okay, so Ishibashi-san, let me confirm your setup and claim. So you put matter only at the boundary and assume no bulk shortcut. Then you can show conformal invariant ANEC. That is the claim. That's correct?
Yes. And the boundary stress energy tensor should be should be supported by the AdS CFT.
Yeah.
Yes. But so basically CFTs.
But in this case, are there any matter in the boundary or in the no matter in the bulk? That is your also claim.
So the bound on the matter as an AdS CFT correspondence can incorporate something, then any matter field that is compatible with AdS CFT correspondence, okay. So obviously strongly coupled large M CFTs are okay. And also inside the bulk, actually I just considered vacuum case, but you can also add any bulk stress energy tensor that satisfies NEC.
Okay. Okay, thank you very much.
Yeah, thank you.
Evan-san, please.
I'm just wondering, is there any, purely CFT way to confirm your, that result? Okay, this positivity of this, NEC operator in the curved background. That T mu times the cube of this, that Jacobi field cube.
Yes.
So, for example, so basically the way we prove this ANEC in CFT is that using this positivity of modular Hamiltonian. And the one main difficulty is that we don't know the exact expression of modular Hamiltonian in the curved background. And but for sure, that if the manifold is slightly curved, then so we can use the perturbative expansion of this modular Hamiltonian to get this approximate form of of this that vacuum modular Hamiltonian. So I think this positivity of this deformed modular Hamiltonian should recover the perturbative expansion of this the perturbative related to the expression you obtained.
Perturbative one. What?
Yeah, so so this eta cube times T mu nu. Perturbative that the perturbative with respect to the metric. So you wrote this something expression like eta cube T mu nu integrated over this the curve is positive, right? And you can consider expanding it expand the Jacobi field with respect to the metric.
Yes.
And so I'm wondering, this agrees with this. I mean that the positivity deformed modular Hamiltonian, the perturbative expansion of the modular Hamiltonian.
Yeah, I haven't considered that situation and the modular Hamiltonian, the perturbation of the modular Hamiltonian, the relation to this. So I don't know.
Yeah, but I think it's clear. That what I can do. Right. I have a concrete expression for the modular Hamiltonian on this flat space.
Yeah, flat space. So it's decoupled from gravity.
Yes. And then so on the curved background, that we can derive the approximate expression of the CFT modular Hamiltonian using this perturbative expansion. And I'm wondering it is that we can compare it with the result you obtained.
So sorry, the question is whether you can consider or compare the perturbative derivation of the ANEC, ANEC derivation and some perturbative argument of this modular.
So I just wanted to have purely CFT derivation of your result. And
I think, so our derivation, I'm not sure, but our derivation is just using the AdS CFT correspondence and analysis entirely inside the bulk, extending to the inside bulk. But I think similar inequalities actually for the cylindrical case, similar inequalities derived by Rosso entirely field theoretic point. I think he also consider some modular Hamiltonian, I think in his paper.
But this is, the modular Hamiltonian in DS or AdS, right?
DS and AdS, and also Lorentzian cylinder. So this static Einstein cylinder case as well. And DS and AdS case, you just get a standard ANEC, but for the closed inverse case, you have
it's a trivial case.
This KNEC, actually some confound weight. Weighted ANEC.
Right.
He derived from the entirely field theoretic method.
Yeah.
But so his work might be related to what you mentioned.
Yeah.
But I'm not quite sure. But
But did you expect that this holds for any CFT or specific to the CFT with the holographic dual? I don't think. That the result is valid only for holographic CFTs.
Well, that I don't know, because we assume that AdS CFT correspondence should hold, and existence of
but somehow you are only using this. You are working within the regime of this Pfefferman-Graham. Which is kind of constrained a lot by this conformal symmetry.
Right. Right.
Yeah. Okay. Thanks.
Okay, next, Tanahashi-san.
Do you know what happens when you include the higher curvature correction in the bulk, like Gauss-Bonnet term? Sometimes that kind of higher curvature correction gives you some correction in the causal structure in the bulk. And I thought that some modification would happen even for the conditions you derived. And do you have any ideas?
I think, for example, so first of all, if you include the higher curvature terms in the bulk, then in that case, I think you have to modify this Gao and Waldo's no bulk shortcut theorem itself. You need some modification. Then, using that modified no bulk shortcut theorem, you could derive similar inequalities. But without doing that, I think maybe it depends on what kind of higher curvature term you introduce. But typically, higher curvature term often violate a neck inside the bulk. In that case, I think no bulk shortcut theorem no longer holds. In that case, I think you cannot derive this type of ANEC using the similar technique.
Then would you expect that it is basically impossible to derive this kind of condition to so is it,
I think more
does it make yeah.
I think an interesting direction is how to say without modifying the Nova short term, if you consider just a higher curvature term, then just consider boundary geometry and using Graham expansion and using this technique, then it's unlikely to get a similar inequality. But interesting direction is first, try to attempt to modify the Gao and Waldo theorem to incorporate a higher curvature term. That is perhaps interesting work. And then once you get such some certain no-bulk shortcut time, well, maybe what is the first test curve, including both boundary metric and bulk metric. If you can identify what is the first test no-geodesic curve in your theory, then maybe you can derive the similar inequalities applying to such a first test node curve. So the point of the ANEC is, in particular, aclonal ANEC is that applying the neck condition to the entire aclonal first test node curve. So identifying the first test node, what is the first test node curve? That is perhaps the important step, important point to take first. I think that's an interesting program to do.
All right, thank you very much.
Thank you.
Okay, any other questions? Okay, so because time is up, let's thank Ishibashi-san again. Thank you very much for your great talk.
Thank you very much. So I should stop the.
Yeah.
Okay.
Okay. And we have about 7 minutes short break. And the next talk will start at 4:30.